Start in just half a minute. Let me see how many I can get in here before we get going.
The test is next Friday, right?
That is correct. Yep. Homework 3 is going to be due on Monday, and the test is next Friday, and I think we'll be back on schedule by then. It'll be multiple choice, 25 questions on lessons 1 through 3. Questions will have the same feel as the homework questions and many of the warm-up questions. I encourage you to, well, the way we would do it if we were in the classroom, it would be a 50-minute exam, and I would let everyone bring in one sheet of notes. I call it a cheat sheet, front and back, anything you want to put on it. Since we're in COVID, I'm letting you take the exam from home. I'm giving you 24 hours, and it's not timed. You can spend as much of that 24 hours working on it as you want. But I still recommend that you put together that cheat sheet. I think you'll learn a lot more from putting that sheet together, forcing yourself to go through your notes, consolidate all the information. We've learned a whole bunch of stuff with still more to go in lesson 3. Just the process of consolidating it and organizing it, you learn a lot from that, and that helps with the exam, I think. Also, the questions on the exam will be in order, just like the questions in the homework, and so that can be helpful as well if you're trying to figure out what equation to use to answer a particular question. It's probably going to be the order that you learn the equations and the order that the equations are in the ebook.
Is there somewhere that we can find all of the warm-up questions?
I will post them once I'm done with lesson 3 material.
Okay, thank you.
I have 1, 2, and 3 in a single PDF. And so once we get through lesson 3, probably the Monday before the exam, I'll post it that evening.
Thank you.
Sure. All right, I'll keep peeking over, and as more people find themselves in the waiting room, I'll let them in. But let's start with our warm-up question. This is from last time. So I'll read through it. I see most of you have already taken a stab at it here. So Young's double slit experiment, we have a single photon of light emitted by an atom. It encounters the double slit experiment, so a barrier with 2 slits, and then beyond that, a wall that is a detector. So we have 2 questions. The first question is, which is true? The photon travels as a particle passing through one slit or the other. Or 2, the photon travels as a wave passing through both slits simultaneously. And then the second question has to do with detection. So the photon is detected on the screen as a particle at a single location, or 2, the photon is detected on the screen as a wave with different intensities at different locations. So answer the first one, answer the second one, append those 2 numbers together into a 2-digit number, and then send that over to the interface here. Now I'll give you, another 10 or 20 seconds. All right, let's see how we're doing. You can keep submitting if you want, but we'll take a look at the numbers. Let's see, the lowest possible was 1, 1. The highest possible is 2, 2. Let's take a look at the numbers here. I think this looks good. Got the histogram, and it's a little close between 1, 2 and 2, 1. But since I'm a little short on time and a majority, at least between those 2, got it right, I won't send you into the break rooms. The answer is 2, 1. Let me admit one more person there. And let me just, again, go over this. This is kind of confusing. It doesn't make intuitive sense, and no one really has a great answer for it. It's just the way the universe happens to work. But here's Young's double slit experiment, same picture that was with the question. But if we send photons of light through one at a time, they slowly build up this pattern, which is the interference pattern. The only way you can get that is if the photon traveled through both slits, diffracted through both slits, and then those diffraction patterns interfered with themselves. So the photon is traveling as a wave, it goes through both slits simultaneously, interferes with itself. But then when it hits the barrier, it is a particle all of a sudden. When we're not looking, light and all particles, it turns out, travel as waves, but as soon as we attempt to detect it, to look, it's a particle. It's one of the great mysteries of science on the smallest scales. We don't have a great answer for it. It's just how the universe happens to work. Admit another person. Okay. So yeah, light travels as a wave, but it's always detected as a particle. And we spent some time talking about this last time. Any questions about that? I mean, if you find it disturbing, that is good because it is disturbing. Again, that's just how the universe appears to work. Okay, let's see. Next in the list, I promised to explain that polarization experiment I did at the very end. So maybe I'll just repeat it really quickly. Let's see, .cam, screen up here. I'll get you all out of the way. And I'll put up a blank page. Blank enough. Okay, so last time, as one of our tests for the nature of light, I guess I can turn this around. We talked about polarization. So there we have a polarizer. And here we have a polarizer that if I put it in the opposite direction, it blocks out all the light because light travels as a wave. If light was a particle, it would still make it through the holes between those two polarizers, but it's a wave, so it needs room to oscillate. And if I put two like that, it doesn't have the room, and so it doesn't get through. But then, just for fun at the end, I took another polarizer, I put it in at a 45-degree angle between the two polarizers, and then light gets through again. Not all of the light, a lot of it's blocked, but some light is clearly getting through. And I decided to give you some time to think about that. Does anyone want to venture a guess? As to how that light's making it through if I put yet another barrier in there between them?
Does it cancel out the effects of like one kind of sheet?
It doesn't cancel it out, but it does something to the light that makes it through.
Does it like return it to its original state?
Part of it. The other class couldn't guess it either, so don't worry about it. The other class focused on the idea of maybe one barrier bends it or changes it or diffracts it so its orientation changes before it goes to the next one. But it's actually a little different than that. It's components. So I can draw it out here. Again, I'm not going to test you on this, but it's kind of a nifty result, so it's fun to think about. So most light coming from space is unpolarized. You have all sorts of different polarizations represented. Some light's going this way, some light's going this way, some that way. And once you put up that first polarizer, only light oriented like this makes it through. And if I put up another polarizer perpendicular like this, then all that will be blocked as well. But instead, if we put up one oriented at a 45-degree angle, what it does is you can take this light wave and break it into two components, one oriented with the polarizer, one perpendicular. So the perpendicular component doesn't make it through, but this component does. It's not as much light. Some of the light does make it through. It's just the component of this that is 45 degrees. Then you can put that final polarizer, which is the perpendicular one, perpendicular to the original. And again, you can break this into two components. This component's blocked, but this component right here makes it through because it's then aligned with that third polarizer. So each time, only the component of the light that is oriented with the polarizer makes it through. If you just have two perpendicular components, nothing makes it. But if you put an intermediate one, it takes its component that can then get through the next one. Anyway, that's the explanation. If you're losing sleep over it, there you go. And any questions? And we'll move on to today's material. Okay. So let's see, we left off last time talking about the nature of light. Since we established that light at least travels as a wave, we still detect it as a particle, but it travels as a wave. That means light has all the various properties that waves do. They have wavelengths, they have frequencies, they have energies, and we wrote down the basic equations relating those things. And in particular, one equation, just to review slightly, was that wavelength times frequency is equal to the speed of light. It's equal to the speed of the wave, but the unique thing about light waves is they all travel at the same speed, which means you can convert. If you know the wavelength, since that's a constant, you can figure out the frequency. If you know the frequency, since that's a constant, you can figure out the wavelength. So with light, you can describe it in terms of frequency, and here we have frequencies increasing to the right, and you can describe it in terms of wavelength. Here we have wavelengths increasing to the left. You can use either or, since the wave speed is the same for all light waves. And so we talked about these different regimes, how they have different names, but really the only thing that's changing is the frequency or the wavelength, whichever way you want to look at it. And by specifying that, you uniquely characterize the wave. Let's see. So new material. Light is, traveling as a wave, but then the key question is waves in what? In fact, let's get a fresh sheet of paper and write that down. So waves, as think back to when we were first talking about waves, the thing that makes a wave is it travels through a medium. A particle is its own medium. It carries itself as it travels from point A to point B. A wave has to go through something. That something can oscillate or vibrate, but it stays put, and it's the energy and the information that makes it through the medium. So what is the medium? If light is a wave, what is the medium through which light travels? And there's the correct answer, which is subtle, and you'll probably only get it if you did the reading. And then there's the answer that almost everyone gives, which is incorrect. I'm actually hoping someone gives that first.
Air.
Air. Well, does light make it through outer space?
Nope.
No, it does. We see stars and things, so it's not. It does travel through air when it's here, but it also travels through the absence of air. So what would the medium be? What could it be?
The electromagnetic spectrum?
Yep, so the correct answer is the electromagnetic spectrum, and that's subtle and will require some explanation. What's the answer that most people give that's incorrect? In fact, I think the book even states this at one point incorrectly. They think the medium is the vacuum. So a lot of people think that, okay, since light travels through outer space and outer space is a vacuum, the vacuum is the medium. But that is not correct, and I just want to emphasize this because the definition of vacuum is the absence of a medium. Vacuum means there's no medium, and so you can't have a wave propagate with no medium, so light waves, they're not propagating through the vacuum. They travel through space, but there's a medium permeating space that they're actually traveling through and not through the emptiness of nothing. And that, as someone said, is the electromagnetic field. So the electromagnetic field is the medium, and the electromagnetic field is what generates the electromagnetic force. So let's just pause for a second and talk about forces of nature. There are four primary forces of nature. The first one, or the one that everyone's most familiar with, is gravity. And this force of nature is attractive, always attractive, and it's between masses. And we've spent a lot of time talking about gravity. If you take Astro 102, we'll talk about it more in the context of Einstein's theories. And then you have the electromagnetic force. We used to think they were separate forces, electricity and magnetism, but they're actually two sides of the same coin. They're a unified force. And the electromagnetic force can be attractive or repulsive. And it's between what we call charges. Put up a figure here, show this. So we call these charges positive and negative, but they're really just opposites. The terms positive and negative, and even the term charge is something that we just applied as a stand-in. They have a property, they have two properties that are opposite to each other. If you have two particles with the same property, the same charge, they repel one another. They have opposites, opposite charges, they attract. So opposites attract. You've heard that phrase in other contexts, of course, and it originates here with physics, with the electromagnetic force. Let's put the dot cam back up for a second. So charges, which can be positive or negative, but again, we could have called it anything we wanted to. We could have called it up and down, black and white, any opposites. And then there are two other forces. Does anyone know what the other two forces are, forces of nature?
The weak and strong nuclear force.
Yep, the two nuclear forces. We have the strong and the weak nuclear forces. And the strong nuclear force is what holds nuclei together. If you think about nuclei, it's a bunch of protons and neutrons. Neutrons don't have any charge, but protons have a bunch of positive charges. And as we just saw, similar charges want to repel. So you have a whole bunch of protons in close proximity. Those nuclei just want to fly apart because of the electromagnetic force, which means there has to be an even stronger force that holds it together against that, and that's the strong nuclear force. And then you have the weak nuclear force, and that's kind of a weird force. It's a little non-traditional. It's responsible for nuclear decay, for changing one particle into another, and there's certain rules by which it operates. Those are more Astro 102 topics. Okay, let's come back to the electromagnetic force here. And as I said, you can view it separately. It has an electric component and it has a magnetic component. Let's focus in on the electric component first. And so this is a field diagram. It's showing the electric field. You can draw these things for the gravitational field as well. Here we have a charge. In this case, it's a positive charge, and we're drawing lines emanating from it. And close to the charge, those lines are concentrated. There's a higher density of lines. That just means the field is stronger, and so it will generate a stronger electric force. And far away from the lines are lower density, or far away from the charge, the lines are lower density, they're spaced out. So you can view that as a weaker field, and hence it generates a weaker force. It's just a way of depicting the strength of the field. Now let's say far away here we have an electron, which is oppositely charged, so it's going to be attracted to this positive charge, maybe it's a proton, and it will start moving towards it, slowly at first because the field lines are low density, that means a weak field, but as it gets closer, the field lines are denser, and so it's a stronger field, a stronger force, and it'll go faster and faster and faster as it approaches the positive charge. Okay, so that's a basic way it works. Now, what happens if we do two things? First, let's confine the electron so it can't move towards the proton. It can move up and down, but not towards the proton. And then let's shake the proton or shake the positive charge. So I'm just going to turn the dock cam around and demonstrate this. There's my table. Flip, flip. Okay, so what we have here is a metal pole. And the nice thing about metal is conductive, which means electrons can flow through it. Like the wires and the walls and everything, that's how we get the electricity to move. It just electrons moving through metal. It's conductive, so negative charges, electrons can flow. Now let's say the styrofoam ball is a big positive charge. Now as long as it's not too strong of a positive charge, it won't pull the electrons out of the metal. The metal's conductive, so the electrons can flow through it pretty easily. But you have to have a really powerful electric force here to pull them off of the metal. Let's suppose we don't have that. So if I take the positive charge and I move it all the way up here, the electrons in that pole, where are they going to move? To the top, yeah. Some of you are probably indicating, but I can't see from here. And if I move it down, then the free electrons in this metal pole will move back down to the bottom. So if I go up and down, the electrons over here will do the same. But it won't be instantaneous. The force doesn't travel instantaneously. It travels at the speed of light. So there will be a delay. I move this up and then the electrons go up. I move this down and the electrons go down. But instead of thinking of it in terms of the charge, think of it in terms of the field, which will be the medium through which light travels. If we have a field line coming out here, right now it's high and then it's low and then it's high and then it's low. So the field line is looking like this as it's approaching the metal pole. So a wave. As I move the charge up and down, I'm sending a wave through the electric field that's emanating from that charge. So you can see that here. If I vibrate, if I shake a charge, I'm creating a wave in its own electric field, and then that will, you see it's getting weaker and weaker the farther out you go, but if there's a distant charge out here, it will then feel that wave and respond to it. And this is light. Again, light is a wave. It has to travel through a medium. The medium is the electromagnetic field. So if you want to make light, all you have to do is shake charge. Physically, that's what it comes down to. And we'll look at some examples of that. Let me bring up my slides here and see what's next. Yep, got it. So here's a common everyday example. I know this is a weird a weird concept, but you make use of it every day. So your cell phones or your car radio, it works the same way. You have a metal rod, just like the metal rod I was showing on my table over there. In your cell phones, you have a little metal bar. We used to pull it out, the antenna, but now they're just built inside so you don't see them anymore. On your cars, you can see the antenna. And then you have a cell tower. And all that tower is doing is oscillating charge, sending ripples through the electric field that's already emanating from that charge. And those ripples are then felt by electrons in the metal bar in your phone. And you can encode, as we talked about, information in these waves. You can modulate the amplitude. So at the cell tower, I could do big oscillations of the charge and then small oscillations and then big oscillations. And I can code information into the pattern of modulating the amplitude modulation, AM radio. And then as those waves propagate out to your phone, the charges in that little rod will respond in the same way. That's an alternating current, and the electronics in your phone can interpret it and extract the information that was encoded and resynthesize the voice. Or frequency modulation, which is, I think, what these towers use. I can't remember, but I think that's the case. So they're taking this charge and they're shaking it at a high frequency and then a low frequency, and a high frequency and a low frequency. Again, sending information through is just reproduced by electrons in the little bar, in the little antenna in your phone. And it can work the opposite way as well. You can shake those and send a signal out that can be picked up. So that's how that information is being sent back and forth. It's because we know light is a wave and we can encode information into it. So that's the electric component. We said there are two components, the electric and the magnetic, and these two always go together. Now we realized this over a century ago, 1 to 2 centuries ago. For example, consider a battery here. It has a negative terminal and a positive terminal, and you can hook up a wire, making a loop. This is a simple circuit, and the electrons, the electricity will flow through that circuit. And so you know, it's flowing like this. And if you have an electric field, if you have electrons moving in a loop, then that will generate a magnetic field. The magnetic field will be perpendicular. You can change a magnetic field to make an electric field. You can change an electric field to make a magnetic field. These two always go together. And a good example of this is Earth itself. Down in the core, as we'll learn once we get back to solar system objects, not the absolute inner core, but the outer core is liquid. It's liquid iron, which is a metal, and it's conductive, so charges can flow. And since Earth is spinning rapidly, that sets up these little eddy currents down in the outer core. Basically loops, just like this. Charges going in loops, and it generates magnetic fields. And those magnetic fields add together to give us our global defense system. Our magnetic field protects us from high energy particles coming in from space and keeps the cancer rates low because of that. So the two always go together, and we'll talk about the generation, how you actually make light in a second, taking advantage of this idea of shaking charge. But I'll just end with this diagram here. This is what a physicist thinks of when you say light. This diagram, a wave in the electromagnetic field. The electric and magnetic components are orthogonal to each other, but it's a wave. In fact, if you want to mess with a physicist, you just run up to them and say light and run away. And this image automatically pops in their head. They can't control it. That's what they think of. I know you've always viewed light very differently, but this is what's going on physically. Okay, so explain this in a second, but how do we make light? Well, from shaking charge. There are all sorts of ways you can shake charge, and different ways give you different distributions of light. In Astro 102, we'll talk about using magnetic fields. If we have a strong magnetic field and electrons get caught in that magnetic field, they'll cycle around, and that's shaking charge, so it's going to send ripples through the electric field, the electromagnetic field emanating from that charge, and you get a certain distribution of light. That's called synchrotron radiation, a synchrotron distribution. In 101, we'll consider a different distribution, one that's a little bit more common, and that is a black body distribution of light. Oh, there's one thing I wanted to show you before I go there. I forgot to do it. I'll just do it real quick. Back on the magnetic field here. And I just want to point out that the electromagnetic force is way stronger than the gravitational force. We don't think about this, but that's the case. And I'll just demonstrate it really easily here. I can pull these magnets apart. There we go. I'll just put one on the dot cam. Okay. And it's being held down by the gravitational field of the entire planet. The mass of all of Earth is holding it down. And yet I can overcome it with just a little piece of metal here. And pulls it up there. And you've played with magnets before. You know how they work. But if you think about it, that's kind of impressive. Just this one piece of metal overcame the gravitational attraction of all the mass of Earth. And that just goes to show that the electromagnetic force is way stronger than the gravitational force. In fact, it is the strongest, or the gravitational force is the weakest of the four forces. Okay, so I was talking about making distributions of light. And I said we're gonna talk about how you make a black body distribution. Let me write that here. Black body radiation, sometimes called thermal radiation. And this has everything to do with temperature. So again, if we're going to make a distribution of light, we're shaking charge in a certain way. So consider, we'll start with like the gas in the room that you're in. Gas in my room here, the gas in the room where you are, the atmosphere. It has a certain temperature, and what's going on in this gas are the particles are moving around. They're bouncing off each other. They're changing the directions. They're changing their speeds. And these little particles have charges in them. So every time there's a bounce, a collision, a change in direction, a change in speed, you're sending a ripple through the electromagnetic field emanating from that charge. It's not a nice, smooth sinusoidal variation, like you're shaking it up, down, up, down. They're kind of bouncing around in a random walk fashion, but every time there's a collision, it's sending a kind of a herky-jerky signal through its electric field, like sending one crack down a whip, and then the next collision and the next. But you're sending information out, you're sending energy out. And this is all a function of temperature. So temperature, what is temperature? It's just the average speed of the particles, average particle speed. So again, the example of the air in the room that you're at, there's a certain temperature you're feeling, and all that's reflecting is the average speed of the particles. Some are bouncing around faster, some are bouncing around slower, but there's an average. And if you were to turn the heat on and start to warm up start to warm up the air in your room, that corresponds to a higher temperature. That just means the particles are bouncing around more quickly. And this figure right here, this is the distribution of speeds that you get. And for any temperature, you have some average speed, and you'll have some particles moving more slowly, and you'll have some particles moving more quickly. The fast-moving ones can become slow-moving ones, the slow-moving ones can become fast-moving ones, but on average, this is the distribution of the gas particles in the air in your room. And it's not just for gas, it's for liquids and solids as well. With liquids, the particles are all really close to each other, in proximity to each other, bouncing off each other continuously. With air, there's separation between them, or gas, there's separation between them, so the collisions are a little bit less frequent. With solids, they're connected by intermolecular bonds, but they're still pushing up against each other. Here's a little demo of that. Here we have a complicated molecule, and it's shaking because it has some amount of energy. I should write that down. Average particle speed is kind of the same thing as the average particle energy. The more energy the particles have, the faster they move. The less energy, the slower. So if I were to take this molecule here and remove energy from the system, the particles would slow down. And if I extract, the particles would slow down, which means the temperature decreases. If I extract all the energy from that, such that all motion stops, what temperature do we call that?
Total zero.
Yep, total zero, absolute zero. And that's all that means, is the particles are not moving anymore. That you can't cool anything down below absolute zero because the particles have ceased to move. You can't have less motion than that. Let's go back to the idea of a gas. I have a demo here, or a simulation. So particles in a box, and the different colors correspond to different speeds, different energies. The yellow particles, the white particles, if you look at them, they're moving the fastest, and the blue and the violet ones are moving the slowest. And if you track them, you'll see they change colors, change their speed, change their energies as they bump into each other. And down here you see the distribution of speeds. And it's a little noisy because I have a small number of particles, but the white is an average, and that matches this distribution over here. And if I pump more energy into the system, speeding the particles up, you still have the same distribution. Remember, this is plotted around the average speed. All the speeds are higher now, but compared to the average, you have that same distribution, like you see over here. And to make it less noisy by increasing the number of particles, it fleshes it out a little bit more cleanly. Okay. So as these particles are bouncing off of each other, as I described, they're sending ripples out through the electric field. The high-speed ones, the particles that are moving quickly, are going to run into things much more frequently, and so you're going to have high-frequency oscillations in their electric fields, and that corresponds to high-frequency light being emitted. And the slow-moving ones generally run into things less frequently, and so you're going to have low-frequency oscillations in the electric field, so low-frequency light. So they're all sending these waves out as they bump into things. And so a certain distribution of speeds corresponds to a certain distribution of light frequencies. And this is the distribution of speeds that you get for a thermal object, gas, liquid, or solid. And you can go through the physics. We're not going to in this course, but if you do go through the physics, it corresponds to this distribution of light. I'm just checking the time here. I have about 14 minutes. Yep, we're looking good. So let's talk about this distribution here. We have frequency increasing down here. Wavelength goes in the opposite direction. Intensity here, and there's some peak. There's a long tail going down to low frequencies and an exponential cutoff at the high frequencies. And here's the same figure with a little bit more detail. First of all, this is a powers of 10 figure. If you look on the x-axis, every tick is a factor of 10 higher. And on the y-axis, every tick is a factor of 1,000, but you can imagine extra ticks there. So if we call this 1, this is 10 times as much light, 100 times, 1,000 times, 10,000, 100,000, a million. So if you go up on this plot just a little bit, it's a lot more light. So that's something to keep in mind. Now, another thing you see here is the visible range is really narrow. Most light is not visible to the human eye. Now, visible light is over a very small range. I'm going to write it down here. So visible light is 400 to 700 nanometers. So that's on the wavelength scale. Down here you can see 400 to 700. It's right around there. Where 400, that's the shorter wavelength. That's over here. So let me write that down. The shorter wavelength, that would be violet, the violet side or the blue side of the spectrum. The longer wavelength, that's the red side of the spectrum. Out beyond red, we have infrared and then microwaves and radio. Out beyond violet, we have ultraviolet, and then X-rays and gamma rays. So let's look at a few of these curves. These are curves of different temperatures. Here we have a 300 Kelvin curve. And 300 Kelvin, that's kind of like room temperature, a little bit warmer, but approximately room temperature, the temperature of you, the furniture in your room, the walls, the air. It's approximately 300 Kelvin. And so you get a distribution like this. It's peaking in the infrared. How do we sense infrared radiation? What do we call it? I think I asked this last time.
Heat.
Heat. Yep, heat. So something that's 300 Kelvin is emitting a lot of heat. Well, it's emitting most of its radiation in the form of heat, in the form of infrared. And then you have this rapid exponential cutoff that falls short of the visible. So something that's 300 Kelvin does not emit its own visible light. You do not emit visible light. I see you, but that's because light is bouncing off of you. That's reflected light. If you don't believe me, find a dark closet, close yourself in there and see if you can see yourself. Consider it a homework assignment, I guess. Now, if you do want to emit visible light, you have to heat yourself up. If you warm yourself up to 1,000 degrees Kelvin, which I don't recommend, it's not good for your health, but if you did, the peak would still be in the infrared, but you see the exponential wing here does cross into the visible. There's not much light, but the light you get is very red. You get some red, maybe a smidgen of yellow, and then hardly anything of the blues and the greens and the blues. So we warm it up, the peak is moving to the right to higher frequencies, and now we get a little bit of red light. So it'd be faint and red. If you heat it up to 4,000, the peak is right at the boundary between visible and infrared, and you still have a lot more red light than blue light. Remember, this is about a factor of 10, so 10 times more red light than blue light. So it will look red, just not as red as this one. Heat it up to 7,000. Now the peak is at the boundary between violet and ultraviolet. You have more blue colors than red colors, maybe by a factor of 3. So it will look blue, just not pure blue. There'll be reds and things mixed into it. And if you go up even hotter, it's not shown on this diagram, but you go straight through at a particular angle and you peak somewhere out here in the ultraviolet. And any temperature hotter than that, although the peak is in the ultraviolet, and we can't see ultraviolet, it does cross the visible, and you have more blue than red, and that particular shade of blue we call thermal blue. So there are two things going on here as we increase the temperature. And I'll write these down, and we'll work some mathematical examples, and then I'll do a quick demo to end the day. The first is the peak is changing as I increase the temperature. And the second is the overall intensity. The amount of light increases at all frequencies, at all wavelengths, as I increase the temperature. Let's take the first one first. So there's an equation called Wien's law, spelled with the W but pronounced with the V, Wien's law. It tells you where it peaks. So the peak wavelength, it's usually written as 0.29 centimeters divided by the temperature measured in Kelvin. But this is not really useful. Again, we measure light in nanometers. Visible light is 400 to 700 nanometers. And sometimes we'll mention in microns where 1,000 nanometers is 1 micrometer, which we call a micron for short. A micron is kind of the boundary between visible and infrared. It's a little bit into the infrared. And so we would like an answer probably in nanometers. So we can restate this as 2,900 nanometers divided by the temperature measured in thousands of Kelvin. Usually with things like stars, we measure them in thousands of Kelvin. So let's work two examples here. First example is, let's say the temperature is 1,000 Kelvin, in which case the peak wavelength would be 2,900 nanometers divided by 1,000 Kelvin over 1,000 Kelvin. And that's just 2,900 nanometers. 2,900 nanometers is longer than 700, so this is peaking where? In the infrared or the ultraviolet?
Infrared.
Infrared, that's right. 700 is the red side, 400 is the blue or violet side, so this is peaking in the infrared, and indeed, here's that 1,000 Kelvin black body peaking in the infrared, but although the peak's in the infrared, it will appear red because some of the distribution crosses the visible part of the spectrum. Let's work one more. Running out of space here. Let's do 10,000 Kelvin. In that case, the peak wavelength is 2,900 nanometers divided by 10,000 Kelvin over 1,000 Kelvin. So 2,900 nanometers over 10, that's 290 nanometers. Is that in the infrared, visible, or ultraviolet?
Ultraviolet.
That's the ultraviolet. So that's peaking in the ultraviolet. And although we can't see ultraviolet, we'll still see that object. Again, if the peak is in the ultraviolet, it means the spectrum has crossed through the visible, and so this will appear thermal blue. I just wrote thermal blue. Okay, let me show you some examples here. Here is something very cold, only 60 Kelvin, a cloud of gas out in space, cold cloud of gas. Its distribution is peaking here in the infrared or even in the radio. So we clearly won't get any visible light. We have to look with the radio telescope and we can see the contours here. It's also full of dust, which is blocking background starlight. That's why it appears dark in the visible. Here's 600 Kelvin, still peaking in the infrared, but crossing into the visible a little bit, and you can see how red that gas is. Here's 6,000 Kelvin. This is our sun. Our sun is actually 5,800 Kelvin. Peaks here between red and yellow, so you'd expect it to be orange. But once you throw in a little bit of green and blue, it gives it this yellowish tint. That's why the sun's yellow. And here's 60,000 Kelvin, which means you're going to peak way over here in the ultraviolet. But again, you're crossing through the visible, so the stars, these hot stars, will appear thermal blue. Okay, that's Wien's law. Let's work Stefans law, and then I'm going to demo this. I might run 1 or 2 minutes over, but hopefully the demo's worth it. So the second feature here, let me go back, is Stefans law. As we increase the temperature, we get more emission at every frequency, at every wavelength. So Stefans law says that the energy flux, what that is, it's the energy emitted at all frequencies per unit time, per unit surface area, the emitting surface, is proportional to temperature to the 4th power. Sorry, I'm writing on the doc cam. There we go. Stefans law, energy flux, which is energy emitted at all frequencies per unit time, per unit surface area, is proportional to temperature to the 4th power. So ratio astronomy here. If I double the temperature, how much more energy is coming off of that object per time per unit area?
Double?
Not double. I'm doubling the temperature. So, but we have temperature to the 4th power. So it would be 2 to the 4, which is what?
16.
16. Yep, again, with this ratio approach, you should be getting to the point where you can look at the equation. If I'm doubling the temperature, I stick a 2 in here, but then I still have to do the math. 2 to the 4 is 16. So if I double the temperature of a star, of an oven, if I double the temperature of an oven, I'm going to get 16 times more energy coming out of it. Any thermal emitter. Okay, I'm going to now demonstrate Wien's law and Stefans law using an incandescent bulb on a variable power supply. And I'm even going to try to show you the spectrum. But first, let's just look at the overall color. So here I have a bulb, and a bulb is just a piece of metal in there. It's a tungsten, an incandescent bulb anyway. It's a tungsten filament. It's a piece of metal with high resistance. So as I run voltage through there, there's a lot of friction. It heats up the metal, and it will glow. So I'll just set that there. And as I turn this knob, I can heat it up. So it's on a low setting now. We're not getting a lot of light. That's Stefans law. But the light that we're getting is very red. In fact, if I bring it down a little bit, it's very, very red. That's probably about 1,000 degrees. That's why they put a glass bulb around it, so you don't touch it and burn yourself. Now, as I increase the voltage, I'm increasing the temperature in the wire, so the color is changing. There we have orange. Now it's getting yellowish. So I'm changing the color. That's Wien's law. And I'm changing the overall intensity. It's getting brighter. That's Stefans. Orange to yellow, and then yellow-white. There's white, and then blue-white. And if I could keep going, it'd get blue, but it cuts me off there because, I don't know, it'd probably explode or something. Now I'm going to try something just for fun here. I'm going to try to show you the spectrum. I'm going to turn this towards me so I can see. What I have here is a grating. And if I hold it just right, you can see the spectrum in there. You see, it's really low right now. But if you look carefully, you can see the reds and the oranges and the greens and the blue. So remember that. As I increase, maybe I'll decrease it a little bit more. I don't know if that'd be enough light for you to see the spectrum, but we'll see here. Yeah. So there I decreased it more. So this is about as much red as we're going to get, but we still have those other colors. But as I increase it, make it brighter, we should see a higher proportion of blue. It's maybe a little hard to see, but there's definitely more blue there than the red. I'll go up even more, and maybe if it gets too bright, it just kind of washes out. Yeah, there's a lot of blue kind of right there compared to the red. Normally, I would pass these out in class and you would all do it yourself. So just the last thing I want to mention here, let's write down that sequence of colors. We had red. I can't see anything after staring at that bright light. Red, orange, and then it went to yellow, and then yellow-white, and then blue-white. If we could keep going, it would be blue, our thermal blue that we've been talking about. But there are no green stars. Now, stars have all these colors just because we're changing their temperature, just like the temperature of that bulb. When that bulb was yellow, it was the same temperature as the surface of the sun. Again, that's why we put it in a glass bulb so we don't touch it. So we go through this sequence of colors, and starting like the rainbow, red, orange, yellow, eventually getting out to blue, but there's no green. And I showed you with the spectrum, I broke it down into the colors. You saw the green in there, but we don't see any green stars. So I want you to think about why that might be, and also watch that video. That's your homework. And so in the YouTube directory, I put a 5-minute video that answers that question. Think about it first, and then check out the answer. And then we'll move on from there next time. Okay, I'll stop, and if there are any questions, I'll hang around.
Thank you.
My pleasure.
Thank you.
Thank you.
Thank you. Thank you.
Thank you.
Would you actually be willing to show the graph that you have behind the dot cam right now?
Thanks.
Going off of the peak wavelength in the graph, how can you, or like at what point is it going to be like a white star versus a blue star?
Yeah, so a white star, and this kind of answers why there are no green stars. Now, when we were going through this sequence here, the dot cam, right where you'd expect green, we see white. So why is that? Why not green? Why white? Got any ideas?
Is it the combination of all the colors sort of washing each other out?
That's right. And so we're not going to spend much time on it next time. That's why I want you to watch the video. But if you look at a star that's just a little bit hotter than the sun, maybe about 6,500 degrees Kelvin, it peaks right here in the middle. And so you have similar amounts of red, green, blue. And so the human eye combines that to be white. If it's peaking in the green, since we also have similar amounts of red and blue, we see white instead of green. That's one of the two answers to the question of why we don't see green stars.
Okay. Also, will we be doing Hertzsprung-Russell diagrams in this class, or is that elsewhere?
That's 102. Yep.
Okay.
This class we end with the, we don't go much beyond the solar system. We'll go a little bit beyond, look at some exoplanets, but we start with stars in Astro 102. Or
Okay.
if you're going to be a major, it'd be 202.
Okay. Thank you.
Sorry, could you go back
Thank
to
you.
the other graph for a second?
Thank you.
Thank you. And while I'm copying this down, I want to ask, the first thing I thought about with the light emissions, is that why when a fire heats up and it gets hotter and hotter, like first it's like a dull red, and then as it gets hotter, it turns into like a blue and a white light? Is that the same thing, or is that something different?
I think that's different because those are chemical reactions. And as those chemical reactions are taking place, I mean, there's some component of it will be thermal, but it depends on what you're burning. You get different colors. In other words, they're emitting the heat part is emitting a thermal spectrum, but a lot of the reaction you're emitting at individual wavelengths, so line emission, which we'll learn about next.
Thank you. That makes sense.
Anything else? Okay,
That should be good for me. Thank you. Appreciate it.
sure. See you next time.